Okay, good morning, everyone, or good afternoon, depending on where you are. My name is Ronnie Mckenzie. I'm a professional civil engineer working in the water loss field, and I'm the previous chairman of the IWA Water Loss Specialist Group. I'd just like to thank Stuart Hamilton and in particular Gary Wyeth for the opportunity to chat to you today, for putting on these webinars. It's a lot of work and I appreciate all the effort they go to make it work. So thanks, Stuart and Gary. Today's discussion is on the sort of quite topical issue of pressure management, which is one of the most important water saving interventions for managing water losses in a potable distribution system. So we'll be talking about that this morning. If you've got a pen and a paper and a scientific calculator handy, you won't need them. I'm going to keep it quite basic. There's no equations, nothing too complicated in it. So I'm just going to give you a nice general overview of pressure management and some of the aspects of advanced pressure control and give you a few case studies. Just to kick off, just to put things in perspective, when we look at leakage from a distribution system, we normally look at burst and background leakage, where bursts are your large leaks and background leakage obviously are your small leaks, which are in every system and are unavoidable. In some countries, and particularly where I'm speaking from, which is South Africa today, we also have a major problem in many areas with high internal plumbing leakage. That's basically leakage in properties through the taps, showers and toilets, where the residents are supplied with water on a continuous basis, but in many cases they don't have the financial means to maintain their pipework within the properties. And as a result, we have some very high internal plumbing leakage, which can often be up in the order of 80%. So it can be quite significant. So when we look at water losses in a municipal system, we tend to look at the three different types of leaks. Just to put things a bit into perspective, I like to show a few pictures of leaks at the start of any presentation, just to give people time to find their way into the system and just to get an idea of what we're talking about. This is a mains burst running at about 50 meters of pressure from an 80mm diameter pipe. This leak was running at 20 cubes an hour and it ran for about 3 hours. So it was fixed quite quickly. It ran up a loss of about 60 cubic meters of water. So it's a big leak, quite impressive, but not a massive loss. This is another one. This is a mains burst on a slightly larger pipe. This leak here was running at 40 cubes an hour. That's what a 40 cube per hour leak looks like. It ran for about 6 hours and it ran up 240 cubes of water. So it's a bit of a bigger leak, this one. Also quite impressive. It's a mains burst. This one here, this is a very significant mains burst. It happened on, I think the pipe in question was over 1 meter diameter and it fractured, and the leak was, I think it was running at about 200 meters of pressure on this particular pipe. It was a bulk transmission main from one of our biggest water utility. You can see it towering above the trees and above the houses. It did get into the news, this particular one. It ran at 200 cubic meters per hour, and it ran for 3 hours. So it lost about 600 cubes of water. It looked a lot worse than it was as far as the water losses were concerned. Now we're on to the smaller ones. This is more of, it's a burst, but it's now a connection burst, as opposed to a mains burst. Now these leaks tend to be a lot smaller, or they run at a flow rate that is much lower, obviously. A typical connection leak will run at about 1 cubic meter per hour, maybe up to 1.5 or thereabouts at 50 meters of pressure. Obviously, if the pressure is higher or lower, it will make a difference. This leak, because it was a connection leak, the water utility didn't really pay too much attention to it. So it ran for about 3 months before the residents finally managed to get the council to come in and fix it, by which time it had run up 2,200 cubic meters of water. So even although it's quite a small leak, it lost a significant amount of water. This is another one. It's the same story. It's a small leak. It was on a connection pipe running into the back of a stormwater drain. It wasn't causing any damage. It wasn't causing any inconvenience, but it ran for 3 years, and it ran up about 13,000 cubic meters of water. So the message on that is it's the run time that you allow a leak to run is extremely significant when it comes to water losses. So I'm sure I'm not saying anything new to most of you. This leak here, this is quite a nice one. This was on a depot that we were working at, and it was a fire hydrant, and someone had stolen a small cap that was on the side of the fire hydrant that would be used for pressure tappings. And this thing ran at about 40 cubic meters per hour. And the value of the cap that was stolen couldn't have been more than 10 cents. So it's interesting, people will steal something worth 10 cents and then allow a leak of 40 cubes an hour to run, sometimes just about indefinitely. When we talk of leakage, sometimes we find it's a bit difficult to get the message over. We try and explain to the politicians percentages. We're not really supposed to use percentages. The politicians can sometimes just about grasp the percentages, so it does mean something to them. We do try the ILI. We try and convince them to use the ILI, but that normally goes over their head and you just get blank stares at you. So sometimes we try and do it using a different methodology. So we've developed our own performance indicator particularly for the politicians. It's actually courtesy of a friend of mine, Prof. Muller, Mike Muller, who is a former engineer, or current engineer really, and a former politician himself. So he came up with this idea, let's express it in terms of a Mercedes-Benz car. And that really gets the attention. So if you want to show how big a leak is in terms that even a politician can understand, we recommend the use of the Mike Muller Mercedes Index. This is it. You can do it on an annual basis as well. That's sometimes even more appealing to the politicians if they think that they might be able to get 12 Mercedes cars out of the deal. Anyway, we're talking today the BABE methodology, the burst and background estimate methodology. As you know, it has 4, when we're looking at the physical real losses, the leakage in the system. On the BABE methodology, you've got the analysis and logging and analysis of minimum night flows. You've got looking at the infrastructure. You've got the economics of active leakage control. How often do you send people in to look for the leaks? And then you've got pressure management, and that's what we're going to chat about today for the next 40 minutes or so. So pressure management, as I mentioned at the beginning, it is probably the most important intervention when you're trying to reduce losses from a water distribution system. If you don't have the pressure under control, anything else that you do will virtually not last. If you go and if you repair leaks or you fix internal leakage, it's not going to last if you don't manage the overall pressure that's causing the problem. Now, it's not always the answer, but in many cases it is a very good starting point. It doesn't fix any leaks. That's an important point to bear in mind. You don't fix leaks with pressure management. You control the leakage and you try to avoid new leaks developing. So pressure management, in our view, is by far the low-hanging fruit for water loss interventions. We always use this picture. This is from a good friend of mine, Ken Brothers. I think everyone uses this one now. This is just a leak from a main at a low pressure, and this is the same leak at high pressure. So basically, what we're saying is pressure drives leakage. If you can get the pressure under control, you will do a lot to get the leakage under control. It's not the solution to everything. It won't solve all your problems, but it will make a good start in most cases. And if you don't have pressure under control, then a lot of the interventions that you try to introduce will not work, or they won't last if you don't keep the pressure under control. Most water supply systems are designed for a certain minimum pressure and at the critical point during peak demand periods. Typically, it's in the order of 20 meters, sometimes 25. It all depends, a lot depends on the firefighting requirements and the particular bylaws that are in the system. But the bottom line is this is what your system looks like most of the time under peak demand. So you might have 60 meters or 50 meters coming into the system, and at your critical point, which is the point of lowest pressure, it's either the point that's furthest away from the system, or it's the highest point in your system, or a combination of the two, depending on how the friction losses work out. At night time, you typically find that the pressure at your critical point will increase, and that is typically when you get most of your burst pipes occurring. That's why most burst pipes tend to occur between midnight and 4 o'clock in the morning, when your system is at its highest static pressure. So when your system, and the other thing is your leaks at night time will run much faster than they run during the daytime. So this is just a schematic that we've got here, an animation. Hope you can see this. No expense spared on this one. It's a Walt Disney production, as you can see from the tremendous graphics. At night time, the water pressure, the static pressure will build up, and your 20 meters at the critical point will turn into 50 meters. And that's roughly when your pipe will burst. So this is, I'm just explaining the obvious to you. Before continuing, we'll just quickly touch on FAVAD. This is an overview of pressure management. So I just want to touch on why the water leakage in some areas is more sensitive to pressure than other areas. You'll often find that when you introduce pressure management to an area, in some cases you'll get tremendous savings, and in other cases you'll get rather average savings. And it's sometimes difficult to understand what is driving that impact. I think Alan Lambert and John May many years ago came up with the acronym called FAVAD, which stands for Fixed Area Variable Area Discharges. Basically, in summary, very quickly, what it's saying is, if you have systems that are made of metal pipes, you typically get corrosion holes, and those holes will remain the same size during a day. Okay, obviously over a year or two, the hole will increase, but over a 24-hour period, that hole remains the same size. So it's a fixed area discharge. As you increase the pressure on a fixed area discharge, the flow through the hole will increase at a square root relationship. So if you double the pressure, you will increase the flow through the hole by about 40%. If, however, you have a plastic pipe system, and in many cases also an asbestos cement pipe system, the leaks tend to come through cracks in the pipe or joints that open up as the pressure increases. So as the pressure increases, the area of the leak also increases. So you have a compounding effect there. And what often happens is, on a pure plastic system, if you double the pressure, the leakage can increase not by 40%, but by 200%, depending on what type of leaks you've got. So those leaks are called variable area discharges. And that is why certain systems are more susceptible to changes in pressure, and why the losses will be more significant in plastic pipe systems than in metal pipe systems. Okay, so I'll just get that out of the way. How do we reduce leakage? Well, through pressure management. What do we do? Well, there's a number of different things you can do. One is you can put a constriction in the pipe. You could use an orifice plate, for example. It's a sort of cheap and nasty option. It does work. There are better options. You can put in a valve in your system, and you can reduce the pressure through a valve, through a control valve. Now, what often happens is many utilities, rather than putting in a pressure reducing valve, a control valve, they'll rather just send people out to an area to throttle the water going into a zone using a normal gate valve. Now, it works. It's a cheap solution, but it's not an ideal solution. Gate valves are designed to be either fully open or fully closed. They're not designed to control flow and to throttle flow. If you use a control valve to throttle flow over a period of months or years, it will start to give you problems, and it will often cavitate at the seal, and it will eventually leak. This is a picture of an old control valve that was used to throttle flow into an area. You can see that at the seat there, the cavitation has eaten through the casing of the valve. So control valves are not the answer. It can be an emergency measure if you need to, but it's not an ideal solution. Ideally, we want to use a pressure reducing valve or a control. It's often called a control valve. We'll call it a PRV today. And a PRV is simply designed to reduce the inlet pressure and give you a fixed outlet pressure. That's what the valve is designed to do. Bear in mind, it can never give you a higher pressure than the inlet pressure. So if you set the valve for 50 meters on the outlet, and the inlet pressure for some reason drops to 40, you're only going to get 40 out of the valve. In fact, you'll probably get less, because there's normally a pressure drop through the valve of about 4 or 6 meters in any case. So a pressure reducing valve cannot increase the pressure. It can only reduce the pressure, and it will give you a fixed pressure at the outlet. When you put in these valves, Normally, the rule of thumb is that you can reduce the pressure to about 1/3 of the inlet pressure if you want to. So if the inlet pressure is 90 meters, you can probably safely use the valve to get about 30 meters. Anything more than that, and you run the risk of cavitation, in which case you might find it more advisable to put 2 valves in series and drop it through the one and then through the other. So there's different ways of doing this. The valve manufacturers will tell you. You get different types of valve. They come in all sorts of colors. I'm keeping it non-technical today, so we'll talk about the green one. You get green ones and light blue ones, dark blue ones, and even red ones, depending on what your mood is at the time. We find that if you're going to put in a control valve, don't skimp on cost. Put in a decent one. You want it to last 50 years or however long. These valves are designed to operate and run for a long time. As long as you service them regularly, they can easily last 50 years or longer. So there's no point saving 5% on the cost of the valve and putting in a piece of junk. So use a decent valve. There's many different manufacturers that all have different aspects. You know, they all have different widgets inside doing different things. We find that any of the good control valves will do the job if they're sized properly. And we often find that it's the servicing and the support from the local supplier that dictates which valve is used. So in South Africa in particular, there's a number. I don't have shares in any of them, unfortunately. Clay valve's a good one. Burmat's a good one, Durot's a good one, Baker's a good one, Singer's a good one. You have some of the real roll seal in America. We don't use these so much because they're a bit difficult to service, so they're not using them as much as they used to. And then you've got some of the real Rolls-Royce ones like WAG from, I think, Germany and Austria. So there's a whole bunch of very good valves. My recommendation is buy a decent one. Don't save money on the cost of the valve because you're looking at the lifetime of the valve, and putting in a cheap valve, it's just not worth it. It's not worth it. There's a Durot, and inside of. I'm not going to talk about what's inside them. They're quite. Apparently, it's really quite simple. My friend Neil Meyer is a colleague of mine. He'll give you a training course on all the bits and pieces and what they do, etc. I just look at the pictures and colour them in. There's another one, Burmat one. It's a take of Burmat. Clay valve, that's one of our favourite. We use a lot of Burmats and clay valves and Singers here in South Africa. It's some good kit. Baker, that's a good one as well. We've used that in a number of our installations. There's this is one of the European ones, the WAG plunger valve. We tend not to use these ones. I haven't seen any of these being used. This is like your serious, it will never cavitate and it will last probably 500 years. So these are pretty serious valves. There's a picture of them. Stainless steel things inside that won't perish for years. Pilots, you get different pilots on the valves. It's a Burmat one, there's a clay valve one. The pilot is used obviously to give you your fixed outlet pressure. So you use the pilot in order to make sure that you get a continuous pressure out of the valve. Now, when it comes to controllers, I mentioned that at night time the pressure builds up and there's periods during the day that you have excess pressure in the system. So you can use a controller, which is an electronic or hydraulic device, in order to control the pressure during off-peak periods. And there's a number of different types of controller that you can use. Time or flow control, you can get closed loop control, self-learning, artificial intelligence self-learning, you can get all sorts of stuff. They all have different advantages and disadvantages. There's no silver bullet fits everything. A lot of it's to do with technical support and whether the guys using the equipment know what they're doing. If it fails, will it fail open or will it fail closed? Sometimes that's a big thing. Has it got remote communication, telemetry? Look, there's all sorts of things. It's like buying a car. Not everyone will buy the same car. Otherwise, there'd only be one car in the world. Everyone likes different things. They do slightly different things. This is I'll run through this quite quickly. This is a 24-hour logging result. The inlet pressure is the red line at the top, and the flow is the yellow line, and the black line is the pressure at the critical point. And what we've done here is we've drawn a line at 10 meters. We've decided 10 meters is the minimum pressure that we're willing to accept. Okay, we've spoken to the fire department. They've said it's okay. We can go down to 10 meters in this zone. So this area that is shaded in grey here represents the excess pressure at the critical point in the system. So what we've got is we've got excess pressure. That means we've got excess leakage. So if we can reduce that excess pressure in some way, we will reduce the leakage. So the first thing we do is we put in a pressure reducing valve and we use a fixed outlet. So we drop the inlet pressure by some number and we bring the pressure down. So this is what we're doing. We're bringing the pressure into the zone. It's going to be a flat line coming into the zone. We'll still get a variable pressure at the critical point, but that minimum now we want to be at 10 meters. So we've basically lowered the whole pressure going into that zone, and we've taken away a large part of that grey area, just with a fixed outlet pressure control. As you can see, there's still a certain amount of excess pressure in the system, particularly in the morning and in the late evening. So we can do a bit more. So we decide, okay, we'll try a time control. So we're going to drop the pressure at certain times of the day. This is using an electronic controller. It's the simplest form of advanced pressure control. It's just a little box with a couple of solenoids in it and some buttons that you press and you connect it to the PRV. And that's what it looks like. You connect it to the pilot. There's a number of different makes around, and we knock off some of that excess pressure. You can see the red line now has changed. So we've got lower pressure at certain times of the day. It's a very simple example. I'm keeping it simple as I can. You can then try something a bit fancier if you've got money and you want to try and save a bit more. Bear in mind, every time you increase the complexity of the equipment, it is more expensive and you've got additional things to break down. So if you use a flow control, you can see here, we're going to have a variable pressure going into the zone. And at the critical point, we expect to get a very stable pressure at the critical point. You need to connect the controller to both the meter and the PRV. So both meter and PRV have to be reasonably close to each other, and they both have to be working. If any of them fail, if either of them fail, then the whole system fails. And you can see here that we've managed to strip off the excess pressure both in the morning and the evening. So using some form of pressure control, using a flow control system, you're able to get a much lower level of excess pressure. And by doing so, you can reduce the leakage. That's the theory. You can also use a closed loop control where you put a sensor in at the critical point and you send information back, or you can put in a self-learning system, artificial intelligence system. There's a number of different systems. It's a bit like a point of diminishing returns and where you feel comfortable. We will often stop at time control. maybe flow control, but I would doubt it. And in many cases, we won't even put in a controller if we don't really think it's worth the effort. There's a number of different hydraulic controllers that you get around. They're quite complicated to look at. I've never tried to program or to install one, but most of the valve manufacturers do have these. I think in certain circumstances, they can be very worthwhile. You just need to have technicians that know what they're doing. I think in a developing country, particularly where we are, where we're just keeping a pilot on the valve without it being stolen is a major achievement. To put in something like this, it would probably last about a week in most of our installations, maybe a day. So we give training. It's important that the client knows what they're doing with PRVs. So they need to be trained up, and you give a lot of, it's good to have a bunch of, we've got some rigs there that we've got PRVs and controllers and all sorts. It's important that the municipal personnel can do it themselves, that they don't rely on an external service provider to fix. This is a job that council should be doing. This is what they're paid to do, and they should be doing it. So anyway, they like this bit of training there, fixing up valves, all sorts of things, all good fun. Couple of case studies. I think you've probably seen this one a number of times, but I'll show it again. It's one of my favourites. Kailicha is down in the Cape. It was the first of the large ones that we worked on. My colleague Peter Flower from the City of Cape Town helped get this one off the ground, gave us a chance of doing something that hadn't been done before. And prior to this installation, we typically looked at zones of 2,000 connections. To try a zone of 70,000 connections was pushing the envelope a little bit, but anyway, it worked out well. My colleague Willem Veerling did the design and did the commissioning of this installation, and it worked very well. It won all sorts of awards for it. It had a payback in those days of 6 weeks. At the current price of water, that would probably be down to about 2 weeks now. You can see we used green valves in this one, and we used the gate valves. We used a blue gate valve and a blue meter, so it was pretty well coordinated. It looked fairly fine, and that was the logging before and after. The average before was 2,500 cubic meters per hour, and we dropped that down to about 1,500 cubic meters per hour. We took 1,000 cubes an hour off, which is about 9 million cubes per annum, doing our bit for climate change. Hourly saving was 1,000 cubes an hour. Another one that we did, this was done by my colleague Neil Meyer. Neil designed and commissioned and built this one. This is, we learned a lot from the Kailicha one. The Kailicha one was the first of its type, so it was a bit of an experiment. This one, we had time to do it the way we wanted, and Neil built what is quite a nice installation. We've had 5 presidents visiting this installation, if you can believe that. Now, that's not quite true, really. If I say a president, I really mean a chairman, like the IWA chairman. So we've had the past 5, maybe even 6. I think Alan Lambert might have visited this one, but I know that Tim Waldron's there, Ken Brothers was there, Bambos was there, Stuart Hamilton was there. So we've had a few past chairman and current chairman of the IWA visiting these installations. So it's a bit of a tourist attraction, second only to the waterfront in Cape Town, I believe. SEBA King, we did a performance-based one. This again was a Willem Veerling one. You can see Willem down there with his hard hat on. observing safety protocol. And there's Tim Waldron. He's auditing it for us, making sure we've done a decent job. So this was another of the big ones. It had about 500,000 residents, 500,000 people were supplied from this chamber. And again, it was about 70,000 connections. And it was quite successful. The minimum night flow was originally 2,800 cubes an hour, which is one of the highest minimum night flows that we've seen. And we managed to build this we had to do it using labor-based construction, which means that everything was hand dug. So you dig it out with picks and shovels, the old way. Cut into the big pipe. That's us cutting into the pipe. That's us welding on a big flange plate. We learned lots from the Kailicha one, so we knew what we were doing by this time. You need those flange plates. You also need to pressure test your installation before you put it in. That's another pointer. If you're going to do a big installation like this, do a test water cut to make sure that you can cut the water off to the installation. That's a very important thing. Don't believe what anyone tells you about the upstream valve being great and it was serviced 40 years ago and it seals completely, because it's a lot of rubbish most of the time. So make sure you test it before you cut the pipe. Make sure you can shut the water off. That's a good pointer. You use a big flange plate because the pipe will not be round. You've got to bash it back into a round shape and then weld the flange plate on. You want to pressure test all your valves and things before you put it in the installation. We found that one of the valves had honeycombing in it, and as soon as we pressurized it, it just blew up virtually on us. So we had to redo some of the casing. Results, we were saving about 9 million cubes per annum, which is quite a lot of water. Those are the savings. It was a performance-based contract over a 5-year period, and it worked quite well. It saved, in those days, it saved about $20 million based on water that was, it's now 10 times the price, the water, I think, 5 times the price. So it would be a lot more today. Savings, again, 1,000 cubes per hour, just like Kailicha. We're going to go, I'll finish off with a couple of case studies, interesting case studies I'd like to just touch on. The first one is to decide, would you put in a controller in this case? Here's a case study. We're going to put in pressure control, but would you add a controller? Okay, so the first study that we look at is an area called Eersterrivier, which is one that we worked on down in the Cape. The pressure, the top line is the pressure going into the zone, which is the blue line, and the red line represents the pressure at the critical point. So you can see there's not a huge difference between the inlet pressure and the critical point pressure. What's quite interesting is the inlet pressure is between generally around 80 to 90 meters, and the critical point pressure is between 60 and 80 meters. Now, I mentioned earlier, we actually only want 20 meters at our critical point, maybe 25 or 30 if you want to be really generous. So it means just looking at the critical point pressure, you can immediately see that we've got a major pressure issue here. We've got too much pressure in this system. So this is the flow logging result for this system. You can see that the minimum night flow is at about 150 cubic meters per hour. The average daily demand is 265. The minimum night flow divided by the average daily demand is significant. It's like, I can't actually see it. So I think it's over 50%. Let's move this little box. Yep, 60%, there we go. That means there's significant leakage in the system. It's a fully pressurized system. So there's definitely scope to do something. We've got very high leakage, very high pressure, and we can do something. So we put in a pressure reducing valve, and we set the pressure reducing valve going into the zone. At this case, we set it for about 47 meters, and we got a very stable pressure profile coming in. So this is now at the valve. Okay, this is now what we get at the valve. So we've cut the pressure into the zone from 90 to about 47 meters. The minimum night flow dropped. It was 150 before. It dropped immediately to 48. So we took off about 100 cubes an hour on this zone. Not as big as Kailicha, but it's a smaller zone. I mean, it's a small zone. The critical point pressure is now fluctuating around 35 meters. Now you can see it's pretty stable. Now, technically, we can drop it further. We could take it right down to 20 meters. We didn't do that initially because to take pressure down at the critical point from 80 meters right down to 20, you'll get a huge number of complaints because people are used to watering the back of their garden from the porch. So you stop them doing that immediately, they'll complain. So you do it a bit, you kind of sneak it down over a period of 5 or 6 months. So this is the first phase. We brought it down to about 35 meters. But the key point here is, look at the variability at the critical point. It's got hardly any variation. This system is actually oversized. I mean, that's the reality. It's an oversized system, and the pressure at the critical point is constant. So you don't need a controller here. There is no sense putting in a controller in this particular instance. So in this case, if you want to drop the pressure anymore, you would just use the fixed outlet PRV. We eventually took out that blue area in pressure, and the blue, that's the saving. You can see the difference in between the flow before and the flow after. It was a fairly significant impact, and that was just using fixed outlet. We wouldn't typically use a controller here unless you want a different pressure profile specific, unless you want to allow a different minimum pressure at night time compared to your minimum pressure during the day. But it's not really necessary. In this case, I would just lock it down using the fixed outlet. On this case, this is an adjacent zone, so it's in the same area. It's an adjacent zone. This was the point. This was the critical point pressure at Langer. You can see here that there's a variation at the critical point of about 20 to 25 meters. So we've got a big variation at the critical point. This is a case where a controller would work. This is a case where it makes sense to use a controller. And that is the pressure that we eventually got at the critical point using bog standard time control. We just used the simplest controller going, and we got a profile like this. You could do better. You could spend more money, put in a fancier controller, and probably get something that's even flatter than this. But at the end of the day, it's not really necessary. And at that, I'll just point out that James Watt invented the PRV. This is James Watt, is a Scottish person, for those that don't know it. Invented a steam engine and all sorts. Well, not a steam engine. He made it work. I think he put wheels on it or something like that. Anyway, he invented the PRV, and that's what the first original PRV looked like. And on that, I would like to finish. Thank you. If anyone's got questions, we'll stop there.
Thanks, Ronnie. That was very good. Very interesting outlook on some of the pressure management techniques. If anybody has any questions, you can type them into the chat function, and I'm sure Ronnie will be pleased to answer them. We've got one already, Ronnie, from Michael, which is, most water utilities, at least in the UK, focus on installing PRVs in DMAs. Based on your case studies, and I think he's talking about the bigger ones that you spoke about first, in your opinion, do you think some utilities are missing a trick and should be looking at putting in more PRVs on transmission trunk mains?
Yeah, it's an interest. It's probably the other way about, actually. I think what was happening was we had a zone that was massive. It was just so big that the first step that we were able to do was reduce pressure to all 70,000 connections from one installation. So we got the biggest bang for our buck on that installation. What needs to be done after that is then move down to zones of, say, 10,000 connections where it makes sense, and to put in a smaller PRV controlling a smaller zone. So what the UK has the benefit of funding. They've got enough money to put in PRVs at smaller zones. In many of our zones, we didn't have that funding originally. So it's a question of where can you get most saving for the least amount of money. And that was why on these big installations, I'm not, as a former chairman of the IWA group, specialist group, I'm not recommending that we go to zones of 70,000 for pressure management. That would be pushing it a bit. Where it works well, but we can still go in and do smaller zones. So I'm not suggesting that the UK is missing a trick by any means. That would not be my message there. Quite the opposite, I think. I think going to smaller zones is probably a very good way to go where it makes financial sense. If you don't have leakage in a zone, if you don't have much leakage in a zone and you're not getting many pipe breaks, etc., then leave it alone. You know, don't fix something that's not broken. But if you find a specific area that's experiencing a high number of pipe breaks on a regular basis, then by all means, stick in a small PRV for that zone. It can be 1,000 connections or 500 or 10,000.
I suppose it depends a lot on the head loss across the zone as well, because as you were saying, in your area, the pipes are oversized, which means that you doing larger zones is a lot easier. Whereas in the UK, where the pipes are probably a bit smaller, you'd have too much variable head loss across the zones, I'd have thought.
I mean, that's also, I've kind of simplified it a bit, but like you're mentioning, it's quite a complicated, I mean, in many cases, the zones have been designed quite well. The one that I showed you that was oversized, that's not the norm, actually. That we don't get that very often. Most of the time, we do get a significant head loss between peak and non-peak demand periods. So, and sometimes you actually find that you cannot reduce the pressure during peak demand periods because there really isn't enough pressure to go around already. And as soon as you put a pressure reducing valve in, you've taken 6 to 10 meters off your pressure. And if you do that in a zone that's already very tight, you can really screw things up quite badly. There are a number of valves that have got a very low pressure drop through the valve. There's a couple of valves that open fully, certain designs that can, I think you only lose about 2 meters of pressure if you open it fully. But those are not the norm.
Yeah. Okay, we've got a question from Ian, which is, as PRVs are a potential source of pressure transients, what are people's views on monitoring the PRV outlet pressure for pressure transients using high rate pressure transient RTUs or data loggers?
Okay, I've heard about this being done. We haven't done it ourselves. I know that there's a number of companies that specialize in these microsecond loggings where you try and pick up transients in pipes. In our experience, where we've had problems with certain companies slamming open valves and slamming closed valves, and it kind of works its way back into the reticulation system. We often find that the PRV is quite a useful, almost dampener of certain water hammer effects. I mean, I do understand that if you're right down, if your valve is clattering against a seat, I think it can put shock waves into your system, in which case your valve, I would guess, would be undersized, oversized, probably oversized or undersized, and it's causing that. I would actually say a PRV is quite a useful thing for reducing water hammer in a network. I mean, I think that question comes from someone that's probably got a million logging results of high-speed pressure transients bobbing about.
Yeah, normally in my experience, PRVs don't necessarily open and close that fast, so they shouldn't be creating a transient most of the time. So but it is probably a good point to actually be measuring transients rather than just because it's being created there.
Yeah, I don't know many people that are measuring pressures at these low, at such high frequency event. I don't. We typically, just to get a normal pressure logging out of a council these days is a problem for us. To actually go down to the super fast logging of transients, they've got such bigger problems at the moment we're dealing with. That is sort of on the back burner. I realize it's an important issue and it can be very significant. So I'm not making light of it, but it's the problems we've got with 80% losses and water hammer. You know, it's like we're just fighting fires most of the time.
Okay. We've got a question from Stephen, which is great presentation, Ronnie. My impression with the, I'm going to pronounce this wrong, the Erster River case is that yes, the minimum night flow was reduced significantly, but also the flow during the peak hours. Did this translate also to a reduction in build volume for the water utility? And how large was the reduction and how did the water utility take this?
It was Cape Town. They're quite good that way. If you can reduce the water at all, they're not too worried about some of the build volume being reduced. In that particular, in a lot of the areas where we've got high leakage going into properties, you often find that sometimes you don't get paid for all your build volume when the leakage is so high. But even if it was being built and we did reduce the leakage, certain councils are quite happy about that because they just want to reduce their overall water demand and provide a more secure service to their staff. So he's quite correct. I did show that some of the daily demand was reduced. So it wasn't just leakage, it was people irrigating their gardens. They irrigate for 2 hours and they now only use half a cubic meter instead of 4 cubic meters. So it certainly did impact on the build volume, but the council took it in their stride. They didn't object. They were actually happy.
But could they sell the water that they'd saved somewhere else and make more money?
Absolutely.
That
well, I mean, you saw Cape Town just about ran out of water completely.
That's right,
they were like they were hitting their day zero. They were desalinated. They were paying 70 Rand a cubic meter to get desalinated water. So any water they could save that they were getting 10 Rand a cubic meter for them, that's a bargain. So they would have been happy for any reduction anywhere. So they weren't worried about the bill. I mean, what will happen in cases like that is gradually they'll just adjust the tariffs up so that to make up for it somewhere else, and eventually you start squeezing the wastage out of it. It was wastage in the system, so any saving on wastage goes, and I mean, even other municipalities, Johannesburg is exactly the same. They don't mind if you reduce the water wastage for a large consumer, even if it hits their bottom line. They want that wastage out of the system. Water's too precious.
And I don't know where you're based, Stephen, but one of the key things you have to think about is whether your water supply to your customers is direct or whether it goes into a tank first. If it goes into a tank first, then reducing the pressure won't make any difference. The customers will still use the same amount of water. It's only like in some countries where people are doing, like Ronnie says, irrigation direct from the main pressure that you would see some reductions.
Yeah, that's also that's a good point. I mean, a lot of the houses in South Africa have a small pressure PRV on the main connection going into the house, so that the pressure going into your house and the water tank doesn't exceed about 30 meters. So even whatever pressure reduction we do on the main system, if we don't drop it below 30 meters, it actually doesn't have a huge impact on it. So, but as I say, I think you picked up, is it Stephen? I think you picked up, he clearly saw that we were hitting the demand. So that was, I didn't want to go into that, but anyway, that's a good point.
And we have one question from Saeed, which is, which type of controller or system do you recommend to control PRVs and maintain pressure at critical points in DMAs?
I don't really want to recommend anyone. I mean, there's a number of controllers about. I think it all depends on the service you're getting from the supplier that is of key. Most of the controllers, our preference is not to use a controller if we don't really see value in it, because adding a controller, it will give you maintenance issues at some point. So it's only if you really need a controller that it's worthwhile. And we typically go for the simplest. We would normally go for time control, or we often use the flow control controllers, but in a time control mode, because you can set the pressures on different days according to a time profile. So we actually quite like a profile for Monday to Friday, and then a different profile for Saturday and Sunday. But other people want a more, almost an artificial intelligent type profile where it's continually analyzing what's going on in the system. I mean, they've both got their place in the world, in my view. The biggest problem that we experience is plumbers coming in and opening or closing boundary valves, and it screws up your whole pressure zone. And if there's a fire, the fire brigade will come and or there's a burst pipe, let's say there's a burst pipe, they'll shut off 10 valves to isolate an area, and then they'll open 6 of them and go home, and you find your pressure zones now all over the place. And if you don't keep on top of that, then putting in a fancy controller is not going to help you. So our biggest problem is people buggering about, excuse the French, it's French language, messing about with the boundary valves, and it changes the pressure profile in your zone, and there's no rhyme or reason to that. So it has to be a really smart controller to figure that one out. So I would recommend, one of the key things we recommend is checking your boundary valves every month to make sure your pressure zones remain pressure zones and aren't totally messed up. So I don't really have a view on which controllers to go for. I like to keep it simple and keep it within the technical capabilities of the client, which in many cases is not brilliant.
Okay, thank you very much, Ronnie. That's the last of the questions. There is a comment from Sharon about transients. And maybe we can get Sharon to give a presentation on transients and whether PRVs help or not. So that will be interesting. But just like to say thanks, Ronnie. That was a very good presentation, and we had some good questions coming in there. And we'll see everybody at the next webinar. Thank you.
Okay, thank you. Thanks, everyone. Okay, goodbye.